Okay, everybody, I'm here to talk about assignment number 9, which was to do this reading guide for chapter 13.2 on solutions and the processes of solutions. So the beginning of this was pretty self-explanatory, where we talked about different ways that we could increase the rate of dissolution. And so remember, dissolution is just another word for dissolving. It's pretty easy to figure this out, but the ways to make dissolving go faster. We can increase the surface area by crushing it. We can agitate it, so we can stir it or shake the solution and it's going to dissolve faster. Or we can heat it up, and so we cause the kinetic energy of the molecules to rise, and so we'll see dissolution happen more quickly that way. But let's focus on solubility. So there's this question, why is there a limit to the amount of solute that can be dissolved in a solvent? So I want to use these paper cutouts to explain why we can only fit a certain amount of solute into a solution. So let's just assume that these paper cutouts represent a beaker full of water, and we're going to add some solute to that at 20 degrees Celsius. So these are water molecules, so the Mickey Mouse head shape. And here's some solute particles. And that could be anything in there. And so when you put the solute into water, the water molecules are going to pull them apart. That's the process of dissolution or dissolving right there. And so if we add more solute, the water is going to tend to want to pull those apart. But because there is an attraction between solute molecules, they're going to want to reform and recrystallize, but water is going to pull them back apart. But I want to recrystallize, but no, I want to pull you apart. So there comes a point where if you put any more solute into the system, the water is going to pull them apart, but they recrystallize faster than water can pull them apart. And so they end up staying crystallized and will sink down to the bottom. Now, sometimes those solutes will trade places. So if these come back together, they might sink down, but then these will immediately go back up and dissolve. These might come together, these might come up and redissolve, and so what we're seeing is the rate of dissolving is happening at the same rate of recrystallizing. So recrystallizing, redissolving, that's happening at the same rate. And so why does that happen? Why can't we just keep adding more and more solute? Well, it's because there's only a certain amount of water molecules to be able to pull apart the solute molecules faster than they can recrystallize. So here's an example. In your book, in the reading guide, you had a chart on page 404 that shows you how much solute can fit in 100 grams of water. So this is solubility of solutes in 100 grams of water, and there's different temperatures here. So let's look at salt, the one we're familiar with, NaCl. So at 20 degrees Celsius, we can fit, for NaCl, we can fit 35.9 grams of solute. So what does that actually mean? So let's say we just want to put 4 grams into 100 grams of water. Well, all of those solute particles are going to be able to dissolve, and none of them will sink back down to the bottom. And so we would call this an unsaturated solution. And so what if we added more solute? So now we're up to 8 grams at the same temperature, same amount of water. Remember that water can hold 35.9 grams of salt. We're only at 8, so we still have an unsaturated solution. Now let's add even more. We put 40 grams into 100 grams of water. Now remember, NaCl at 20 degrees can only hold 35.9 grams. So I put 40 grams in there. So that means that not all of that salt is going to, so sorry, it's out of focus. Not all of that salt is going to dissolve. We know that 35.9 grams of it will dissolve, so 35.9 grams, but the rest of it's just going to sink down to the bottom. So that would be, what, 4.1 grams. 4.1 grams is sinking down to the bottom because only 35.9 grams can fit. So what that means is we have recrystallization happening and we have dissolving happening at the same rate. So the term for that is dynamic equilibrium, where the solute is dissolving at the same rate that it's recrystallizing. So that's the point at which the solution is considered to be saturated. We can't put any more solute in there because it'll just recrystallize and fall to the bottom. So in this case, salt is saturated. The solution of salt is saturated in 100 grams of water with 35.9 grams of solute. Any more than that is just going to sink to the bottom. Now, every substance has its own solubility. So let's look at a different one. Let's look at Li2CO. So that's lithium carbonate. Now look at 20 degrees. It can only fit 1.33 grams of solute into 100 grams of water. So let's talk about why. Why is that so low? So here's an example of lithium carbonate. So I put in just half a gram in there. So this would be unsaturated. And if we add some more, so now I'm up to 1 gram at 20 degrees, it's still unsaturated because how much can this water hold? If it's lithium carbonate, it can hold 1.33 grams according to the chart. So I put more than that, I put 2 grams in. So we know that 1.33 grams will dissolve, but we also know that some of the extra will fall to the bottom. So that would be, what, 0.67 grams of extra solute would just sink to the bottom, and only 1.33 grams would actually dissolve. So why is that? Let's think about what's going on there. So let me get rid of this salt, and here's some Li2CO3, some lithium carbonate. So it has to do with attraction. Water's going to be able to pull apart some of these, but remember, they want to come back together, but there's enough water particles to keep them separated. So let's put some more in there. Well, water can pull those apart too, but they keep wanting to come back together more strongly than salt would. Now, if we keep adding solute, at this point, there's just not enough water molecules to keep them separated. They're going to want to recrystallize, and they're going to recrystallize faster than water can pull them apart. So we've got all these crystals hanging out at the bottom. And so with lithium carbonate, there's just not enough water in 100 grams to be able to keep more than 1.33 grams separated. Any more than that, and the solute's just going to sink to the bottom. And that's because lithium carbonate has a much higher attraction for each other than NaCl does. Okay, so what does temperature have to do with this? So we've only looked at 20 degrees, but you see this chart for temperature in degrees Celsius, it goes from 0, 20, 40, 60, 80 up to 100. So how does temperature have anything to do with this? So remember, the higher the temperature is, the more things vibrate and wiggle, and the easier it is for them to pull solute particles apart. So the hotter it is, the more solute usually can dissolve. So that means that solutions are saturated with different amounts of solutes at different temperatures. So let's look at the example of silver nitrate. So silver nitrate is the first one on this chart. So AgNO3. So you can see at 0 degrees, we could fit 122 grams of AgNO3 into 100 grams of water. And then we can fit more when it's warmer, more, and we could keep putting in more solute as the water gets warmer. So here's AgNO3 at 20 degrees Celsius. We can put 216 grams of AgNO3 into 100 grams of water. So let's add more. So I'm adding more AgNO3. I've got 300 grams in there in 100 grams of water. Will that all dissolve at 20 degrees? AgNO3, 20 degrees? No, only 216 grams will dissolve. So that means that, what is that, about 84 grams are just going to fall to the bottom. All this down here is 84 grams of AgNO3 that won't dissolve. So 216 grams will stay dissolved. Now what if we heated this up? See what I did? I heated the solution up. And now look at, there's nothing sitting at the bottom. Why is that? At 60 degrees, there's AgNO3, 20, 40, there's 60. It could actually hold 440 grams of solute at that temperature. There's only 300 in there. So this solution could actually even hold more than 300 grams. So it all dissolved. So this is now unsaturated again. At 20 degrees, this was saturated with 300 grams, but at 60 degrees, it's unsaturated. Now, what would happen if we let it cool back down to 20 degrees? So there, it cooled back down to 20. Look what happened is it became saturated again. Saturated. Because at 20 degrees, remember, the solution can only hold 216 grams. So there's 84 grams fell back down to the bottom. So there's an interesting phenomenon with some solutes. Not all solutes do this. But what if we took this unsaturated warm solution and we let it cool down, and instead of this happening, what if it stayed dissolved? So at 20 degrees, there's 300 grams that are dissolved. It shouldn't be dissolved. It should only be 216 grams, but there's 300 grams dissolved in there. This is called a super saturated solution. So it's super saturated because it has more solute than should actually be allowed to be dissolved. So let's look at what's going on there with these water particles. Okay, so let's say we have a whole bunch of solute sitting down here at the bottom, and then we heat that up. So we heat that up so that it can all dissolve pretty well. And then normally if we let that cool down, they would recrystallize and sink back down to the bottom. But in this scenario, we're saying no, they're just going to stay dissolved. Okay, that's a supersaturated solution. So usually all that takes is for one solid piece of crystal to enter the system so that these have something to grow on. So right now there's no surface for the crystals to grow on. So if I just add one solid piece of crystal, all of a sudden all of these molecules now have something to attach to and grow crystals, and they'll fall back down. So let me show you a video of that. There's a solute called sodium acetate. And this is a supersaturated solution of sodium acetate. It was heated up and then cooled back down, so there's more sodium acetate dissolved than should be allowed. So watch what happens when we put just a little piece of crystal in there. All of a sudden, all those solute, the extra solute particles that shouldn't be dissolved, are recrystallizing. So we're seeing recrystallizing happening faster than dissolving is happening. So this isn't ice, it's actual crystals of sodium acetate that are growing in the solution. So you can actually do this with sugar. This is how they make rock candy. Okay, so what I'm going to have you guys do is I'm going to give you a chart that has 6 different solutes, and it's going to show you what...
Hello, today we have a wonderful experiment, hot ice.
Okay, it's going to show you 6 different solutes that can dissolve at different temperatures and how much can dissolve at different temperatures. I'm going to have you graph those. So you can set your graph up to look just like you see it here. And on my website, I'm going to post the chart for you to graph the points on.